I'll show you how tornadocash protects your privacy in this video. Assume Alice transmits 100 Ether to a different address. On the blockchain, this transaction is recorded. Everyone in the world now knows that the address Alice sent the Ether to now owns 100 Ether since the data on the blockchain is public data. People all over the world can deduce that Alice still possesses 100 Ether if they know the address belongs to her. Similarly, if the receiver of this address belongs to Bob, then the entire globe is aware that Bob now owns 100 Ether. So how does tornadocash keep your personal information safe? How does it manage to keep the sender's link hidden from the receiver? Let's start with an explanation of how deposits function with tornadocash. She'll have to choose two random numbers, a secret and a nullifier, before depositing into tornadocash. The hash of these two random numbers is then computed. She'll send the 1 Ether, the hash of the secret, and the nullifier to deposit into tornadocash. Let's call it OX123. In the tornadocash contract, the Ether is stocked. The smart contract also keeps track of this hash, which is referred to as the commitment. This hash will be used to withdraw 1 Ether from tornadocash later. Tornadocash users are constantly depositing and withdrawing funds. We'll pretend that Charlie the cat deposits 1 Ether as well, using the hash OX456. The Ether is converted into tornadocash, and the hash number OX456 is recorded as well. Bob the bear follows suit, sending 1 Ether with the hash OX789. Ether is locked, and the smart contract records his hash of OX789 as well. You may have observed that Alice, Bob, and Charlie each put down 1 Ether. Why are so many people depositing their Ether? Why is it that all of them can only deposit 1 Ether? Assume Alice has 100 Ether, Bob has 1 Ether, and Charlie has 1 Ether to answer this question. They are all putting money into tornadocash. An unidentified user appears later and withdraws 100 Ether. We know Alice was the only person who deposited 100 Ether, thus we may assume she still has the 100 Ether. As a result, everyone must deposit the same amount of Ether into tornado currency to maintain anonymity. As a result, no single user stands out from the rest of the group, and as such, everyone must put in the same amount of Ether. Let's take a look at how tornadocash withdrawals function. First, let me show you how it's done incorrectly. We'll first withdraw in a way that betrays the withdrawal's identity, and then we'll figure out how to solve the problem so that the withdrawal's identity remains hidden. The incorrect method of withdrawal is one that reveals the secret and the nullifier. The smart contract verifies that the hash of the secret and the nullifier equals OX123 before recording it in the tornadocash smart contract. If that's the case, tornadocash will return the 1 Ether to the caller. However, the identity of the person who withdrew is revealed during this process. How does the identity of the person who made the withdrawal become known? Let's have a look at what we got. Alice made a deposit using the hash code OX123, as far as we know. Later, an unknown person revealed a secret and a nullifier, resulting in the hash of OX123 for the secret and nullifier. However, since the hash function is a one-way function, Alice is the only one who knows the secret and nullifier that hashes to OX123. This is how the user's identity is exposed during the withdrawal. So what are our options for resolving this issue? We all know that exposing the secret and nullifier reveals the withdrawal's identity. If there is a way to prove that I know a secret and a nullifier without revealing the actual secret and nullifier, the anonymous user will send the proof that says he knows the secret and the nullifier, such as the hash of the secret and the nullifier is recorded on the tornadocash smart contract. And this evidence hides the nullifier and the actual secret. As a result, the anonymous user will remain anonymous. The smart contract checks the validity of the proof. However, it has no way of knowing whether the evidence is for OX123, OX456, or OX789. In other words, the proof does not reveal the anonymous user's identity. The term for this is zero-knowledge proof. It's the ability to demonstrate that you know something without divulging any details about the topic. The math underpinning the tornadocash zero-knowledge proof is known as ZK-SNARK. Now notice that we chose two random numbers, the secret and the nullifier, when we deposit and withdraw. What is the purpose of this nullifier? When a user withdraws money from tornadocash anonymously, tornadocash has no way of knowing who is withdrawing money. Alice, Bob the bear, or Charlie the cat might all be the withdrawer. As a result, tornadocash is unable to keep track of who has withdrawn their funds. Okay, Tornadocash doesn't know who withdrew, a skilled hacker may say, so what I'm going to do is to try and deposit once and withdraw several times. The hacker sends a proof of withdrawal, which is approved, and the hacker receives 1 Ether. The hacker then sends the identical proof and withdraws 1 Ethereum once more. The hacker is only invested in 1 Ethereum in total, but he was able to remove 2. You deposit it once to avoid duplicate spending, but you can withdraw it several times. When you send the proof to withdrawal, you'll also have to send the nullifier hash, and the SK snark will check 2 items inside the evidence. It would verify that the hash of the secret and the nullifier are both stored on the tornadocash, as well as the nullifier hash is equivalent to the nullifier's hash. When the proof passes, tornadocash records that the nullifier's hash has been spent. The anonymous user receives 1 Ether, and if the same person tries to withdraw using the same proof again, it will fail because the nullifier hash has already been spent and is recorded on the tornadocash smart contract. The nullifier's main purpose is to avoid double spending. So let's have a look at how tornadocash stores the hash that the user provides when they deposit. The Merkle tree is used to store the hash in the tornadocash. The Merkle tree in fact resembles an upside down tree. The root is at the very top of the tree, while the leaves are at the very bottom. Let's take a short look at how the Merkle tree is constructed. We begin by creating an array with each entry containing a hash of some data. We compute the hash using the first 2 elements. We compute the hash for the next 2 elements as well. This method is repeated until all elements have been hashed. We repeat the process after the bottom elements have been matched in hash. So we take the first 2 hashes and hash them again, and then repeat the process with the next 2 hashes. This method is repeated until only 1 hash remains. The Merkle root is what it's called. The Merkle tree is initialized like this in tornadocash. Each leaf is a 256 hash of the string tornado at the bottom. This is going to become ugly, so I'm going to relabel these hashes to explain how insertion works in the Merkle tree of the tornadocash. The very bottom hash is Z0 as we would call it. They're all called Z1 on the next level and then Z2 on the following level. The Merkle root will be referred to as Z3 because this tree has 3 levels. So let's have a look at how to add it to the tornado Merkle tree. This is the Merkle tree of the tornadocash before anyone deposits. We'll say the first person deposit and picks a secret as 0 and the nullifier N0, hashed it together and came up with the commitment C0. The hash of the secret and the nullifier of that user are put as the initial items of the array when the first user deposits the commitment. As a result, the hash above will need to be updated. After that, we will need to update the hash above it, and then we'll need to change the Merkle root's hash. When the first user deposits, the Merkle tree will look like this. Let's see what happens to the Merkle tree when the second user deposits. As a result, the second user will devise a secret. It will be known as S1 and the nullifier will call it N1, and we'll call the hash of S1 and N1 C1. This gets inserted into the next available slot, which happens to be immediately next to C0. So we'll have to recompute the hash above, and then we'll have to recompute the hash at level 2. Finally, the Merkle root will need to be recalculated. This is how the Merkle root will alter when the third user deposits, so we'll add C3 here, which will update the hash on both the first and the second levels. Finally, the Merkle root can be found here. Similarly, it will update the hash on the same levels for C4, when the fifth user deposits, and the sixth, and so on. The Merkle tree will look like this. So that's how tornadocash handles Merkle tree insertion. So now that our hash has been stored in the tornadocash Merkle tree, how can we establish that our commitment is true and that the hash of our secret and nullifier is in the Merkle tree? Let's imagine we have a hash of C3 and we want to show tornadocash that this Merkle tree has our hash. The main notion is that we give it a list of hashes, which will match the Merkle root hash when hashed together. As a result, beginning with C3, we'll need to give C2. We can recompute this hash using the 2 hashes. We'll need to submit this hash and we can recompute it with these 2 hashes. Finally, we can recompute the Merkle root if we supply this hash. These are the hash lists that we need in order to establish that C3 is present in the Merkle root. This hash over here has C3, C2, and this hash over here has C3 and C2, and this hash over here has C3 and C2, and this hash over here has C3. And if we submit the correct number of hashes, the Merkle root of the tornadocash should match. This proof is passed into the ZK snark, which generates 0 knowledge proof, which means we're showing that C3 is in the Merkle tree of the tornadocash without revealing our hash, which is C3. So once we have the proof, we send the tornadocash, and if it passes, it indicates we are able to construct the correct Merkle root of tornadocash. After that, we can withdraw 1 Ether. Let me explain how tornado currency smart contracts are created. There are 3 distinct pieces to the tornadocash smart contract. It has a section that manages incoming and outgoing traffic, a Merkle tree that keeps track of deposit hashes, and a ZK snark that verifies contracts. It confirms that the withdrawal has a valid Merkle tree proved. This ZK snark certifies that our smart contract was created with the help of 2 different tools. The first library is called Circum, is this library that is used to create the arithmetic circuit. The reasoning in this arithmetic circuit proves that the hash is included in this circular tree. We pass the arithmetic circuit onto another program called Snark.js, which uses it to generate a ZK Snark smart contract automatically. But that's going to be it. Thank you for watching, and I'll see you later.